Welcome back, AP Stat. This is part 4 of chapter 19. We're going to be performing a hypothesis test for a population proportion, reviewing all the steps necessary. So here is our situation. Advances in medical care, such as prenatal ultrasound examination, now make it possible to determine a child's sex early in a pregnancy. There is fear that in some cultures, some parents may use this technology to select the sex of their children. That is, of course, a dog whistle for something. A study from Punjab, India, reports that in 1993, in one hospital, 56.9% of the 550 live births that year were boys. It's a medical fact that male babies are slightly more common than female babies. That is true. The study's authors report a baseline for this region of 51.7% male live births. So you may have learned in biology that the Punnett square yields 50% male, 50% female. It is actually slightly higher for men, and that is very complicated, that whole discussion. But is there evidence that the proportion of male births is different for this hospital? So let's look at the hypotheses here. We're going to let P be the proportion of male births. Then our null hypothesis would be P equals 0.517 versus P is not equal to 0.517. Where's that 0.517 coming from? Well, that is our baseline. That's our P sub 0 value. We're comparing our results to this number to see if there's a significant difference. All right, now we're going to proceed to the model. We can use a normal model to perform a one proportion z-test if the following conditions are met. So let's make sure we can use a z-test, okay? Independence assumption. There is no reason to think that the sex of one baby can affect the sex of other babies, so births can reasonably be assumed to be independent with regard to the sex of the child. Independence we can assume, but to further confirm we can use independence, let's go to the randomization condition, all right? 550 live births are not a random sample necessarily, all right? So we got to put a little asterisk next to our results. So I must be cautious about any general conclusions. I hope this is a representative year, and I think that the births at this hospital may be typical of this area in India, so says our textbook. All right, so there is a big if here. These were not randomly selected, so that may introduce bias. All right, 10% condition, that's the other ingredient. We need randomization and 10% condition to conclude independence. So here we go, 10% condition. I would like to be able to make statements about births at similar hospitals in India. These 550 are fewer than 10% of all of those births, obviously so. Let's look at the success-fail condition. N times P sub 0, 550, times a P sub 0, our baseline of 51.7%. is 284.35. N times Q sub 0 is going to be 265.65. It is more than okay that these are decimals. They just need to be bigger than 10. They're a lot bigger than 10. I expect the births of at least 10 boys and at least 10 girls, so the sample is large enough. All right, so we have met our conditions for independence and also our success-fail condition. To confirm, we can do a one proportion z test to determine if the difference in the number of male babies is significant. All right, so now I need to find a p-value, and here's where we will need to go to the calculator. All right, let's go to the calculator here. We will need to go to stat, we will need to go to tests, and we're going to need to go down to one prop z-test. Here we go. So we have our P sub 0 value, and that's going to be that 0.517 number. And now we have X. This is the number of observed successes. In this case, that would be male births. That would be 56.9% times my 550. Which is going to get me a decimally number. So that 0.95, a person's a person no matter how small. So we would say 313, all right? We would round appropriately. N is equal to 550, and we are looking for a significant difference of some kind. So we would say P is not equal to P sub 0. P is not equal to 0.517 is our alternative hypothesis. And we go to calculate. And there we go. We have our p-value of 0.01. So that is a 1% chance of getting data as extreme as ours if the null hypothesis is true. So that casts some doubt on our null hypothesis. So we have a p-value of about 0.014. So what does that mean? Well, let's look at this graph here. A result as far away from our assumed population proportion as 56.9% yields a p-value of 0.014. Now, note we are looking to see if there is some sort of significant difference. That p-value then would mean there is this likelihood of a significant difference going either way, all right? So this p-value means the likelihood that we got a value this far out either on the left or the right-hand side would be 0.014. So half 0.007 is on either side, all right? Because these are the odds that we are this far out on one side or another, not just on one side. So in a sense, we split the p-value between the tails. That explains why this p-value is mysteriously split between the two sides of the bell curve, right? So that's what this little description down here is about, just for clarifying purposes. This is for a two-sided alternative. All right, so we need to summarize our results by interpreting the p-value in the context of the problem. Here's how the book does it. The p-value of 0.0146, we just get one place more accurate each time, I guess, says that if the true proportion of male babies were still at 51.7%, then an observed proportion at least as different as 0.569, 56.9% of male babies, and that is at least as different on either side, would occur at random only about 15 times out of 1,000, okay? Yeah, if we were to round up to that value 0.0146, round that up to about 15%, that would be 15 in 1,000. That is not a likely event. With a p-value this small, I reject the null hypothesis. There is strong evidence that the proportion of boys is not equal to the baseline for that region. It appears that the proportion of boys may be higher, right? And of course, a hypothesis test cannot say why. It can just say that it appears to be higher. Okay? Now, there is an additional step that we can use. This is a confidence interval. Okay, suppose we worked in HR for a company and needed to hire more workers and agreed to pay the new hires 1.5 times the original starting salary. That's pretty awesome. Let P be defined as the likelihood that we could fill the role in 2 weeks. All right, so what are the odds we can fill the role in 2 weeks? We found was 60% before increasing a starting salary. So baseline, 60% chance we can fill a role within 2 weeks at this job. That's before this new offer of 1.5 times the original salary for new hires. Okay, so consider if our p-value after changing the salary were 0.003. That means the salary change is good, right? If we're seeing if we can fill a role within 2 weeks at a higher rate, well, that low p-value here means that, yeah, I think this new strategy that we're using, increasing the pay, is giving us a result that is significantly different and in the positive direction relative to this 60% baseline. So a small p-value means there is a significant difference to that 60%, and that in the positive direction. We're doing better at fulfilling a role within 2 weeks. So that means the salary change is automatically good, right? Well, not necessarily. The plot thickens a little bit. Our confidence interval might be useful here. We can determine where P would be likely given a confidence interval. So that's between 62 and 65% that is where we think the true population proportion would be after this change happens, okay? So here's the big question. Are we going to increase salaries by this much if our result is significantly different than 60%, but only at most by a difference of 5%? I don't know if that's a big idea. So is our result significantly different than 60%? Apparently, yes. That p-value seems to say as much. But what does significance look like? 5% at most? Even if it is significant, I don't think it's worth making that change. That's just too much of a cost. So that's probably too small of an increase from 60% to justify altering the starting salary by that much. What we would say here precisely is that the effect size, well, what's the effect size? That's the distance between the true location of P and the location of P naught, is too small to make a change worthwhile. P, we're saying, is very likely to be between 62 and 65%, all right? So our effect size would be between 2 and 5% relative to our 60% baseline. That's a small effect size, all right? So even with a statistically significant result after a hypothesis test, a confidence interval is helpful. So this is why it's good to consider a confidence interval along with a p-value. A p-value helps us to perform a hypothesis test to determine whether there is a significant difference relative to our baseline, our p sub 0 value. But a confidence interval tells us where the true proportion actually most likely is. It's good to have both. So let's apply that to our example involving fertility in a certain region of India. Statisticians have found that it's best to pair a p-value with a confidence interval, all right? So that is a step 5, and I'll put an asterisk there. It's not part of a hypothesis test, but it is helpful to pair with a hypothesis test. If the true proportion is different than our assumed population proportion, it might be helpful to know where p is likely to be, which the confidence interval tells us, all right? So if there's a significant difference, where is the population proportion? Okay? For example, though our p-value leads us to reject the null hypothesis, the 95% confidence interval for the true proportion of male births in this part of India is in that interval right there. Okay, so that's my 95% confidence interval. We're 95% certain that, that p is between about 53 and 61%. The confidence interval tells us we can be 95% sure that the proportion of males born in Punjab is about 1% higher than expected at very least, which for population demographics, especially in the most populous part of the world, the most popular nation in the world, most populous country as of now, that is a big deal. 1% is a massive deal. Let alone a difference that is significantly higher if you look at that upper cutoff there. All right, so pairing that confidence interval along with our hypothesis test is a good 1-2 punch in statistics, and we'll see that a lot as we go on through the year.